All right, so the ideal gas law. The ideal gas law is derived from the other laws, Avogadro's, Boyle's, and Charles, when you combine them into one. So we have Avogadro's, V over N, V1 N1 equals V2 over N2. Boyle's, V1 P1 equals V2 P2. And Charles, V1 over T1 equals V2 over T2. So these are the three gas laws, the ABC gas laws, Avogadro's, Boyle's, and Charles. So that's how I refer to them, as the ABC, Avogadro's, Boyle's, and Charles. Okay? So these ABC laws, if you combine them into one gas law, then you get V1 P1 over N1 T1. Okay? So I've combined all the laws into one, and they will no longer equal V2 P2 N2 T2. They will equal a constant number, R. Okay? And R is equal to 0.0821 liters, atmospheres, over Kelvin moles. Okay? For the units, those are the units. You can see that, right? Liters, atmospheres, Kelvin, moles. Those are the units of R. That's how I get those. Okay? So this is now a constant that I can use in this ideal gas law equation. R. R is 0.281. I'm sorry, 0.0821. And so if I rearrange this whole equation here, I can say that PV equals, bring N and T up here, nRT, and I get the ideal gas law. PV equals nRT, that's the ideal gas law. Okay? So using this ideal gas law, okay, I no longer solve for change. So I'm not looking for P1 to P2 or V1 to V2. I am looking for what is the pressure or what is the volume of this system, because they no longer equal something else. Okay? They equal R. Now I said earlier, in a few slides earlier, back here, okay, that at a pressure of 1 atmosphere, a temperature of 0 degrees Celsius or 273 Kelvin, a gas, if you have 1 mole of a gas, of any gas, it will always equal a volume of 22.4 liters. So this has to do with the ideal gas law. So PV over NT equals R. So if the volume of a gas is 22.4 liters and the pressure is 1 atmosphere, the moles are 1 mole, and the temperature is 273 Kelvin because it's 0 degrees Celsius, then what should they equal? .0821 liter atmospheres, Kelvin moles. And in fact, they do. So 22.4 divided by 273, you're going to get 0.0821 as your answer. Okay?
Once again, what did you get the 22.4 liters from?
That's the volume of any gas at 1 atmosphere, 273 Kelvin, and 1 mole. Okay? And the reason is because it is a constant of 0.0821. Okay? And we'll see that in another way here in a second as well. Right here. Okay? So what if I wanted to solve for the volume instead of having it? What if I solve for it? Well, if I solve for it, now PV equals nRT. PV equals nRT. I want to solve for the volume equals nRT over P. Volume equals nRT over P, so I get volume equals the moles, 1 mole. R is a constant, it never changes, 0.0821 liter atmospheres over Kelvin moles times my temperature of 273 Kelvin. My moles cancel, my Kelvin cancels over a pressure of 1 atmosphere. My atmospheres cancel. I'm left with liters, which is what I want. So 0.0821 times 273, the volume is 22.4 liters. Always. Okay? For any gas. So now we've seen that in a few ways. So hopefully what you're noticing is that with the ideal gas constant, you are no longer dealing with changes. You're dealing with what is the pressure, what is the volume. Okay? You're trying to identify the thing that you want. What are the moles? What is the temperature of this gas? Okay? So it's not what is the new temperature or what is the new volume, it's what is the volume. Okay? So this ideal gas law allows us to calculate those parameters based on the other information that we would have. So now I have volume, pressure, temperature, all and moles all in one equation, and it equals a constant. It's called the ideal gas law. Okay? So let's practice using it. What is the volume of gas occupied by 5 grams of methane at 25 degrees Celsius and 1 atmosphere? Okay, what do I want to solve for here? Volume. PV equals nRT, V equals nRT over P. I just bring P down, right? Volume equals nRT over P. So, volume equals N. What is N? Okay? So what do I put there? Yeah, they didn't give me the moles, they gave me the grams. So, but that's okay because guess what? I can easily convert grams to moles. So 5.0 grams of CH4, and I'm going to convert that to the moles of CH4 from the grams of CH4. So grams and moles, moles are always 1. What are the grams? Okay? So what are they? 12 plus 4? 16 grams. So 5 divided by 16? 0.3125 moles. So now I can put my N in, right? N is 0.3125 moles. What is R? 0.0821 liter atmospheres over Kelvin moles. Okay? What is my T? Good.
Oh, you have to add. Oh, okay.
298 Kelvin. It has to be in Kelvin, right? I can't have it in degrees Celsius. I can't have it in degrees Celsius. So I have to convert it to Kelvin by adding 273. Okay? So, what is my pressure? 1 atmosphere. My atmospheres cancel, my Kelvin temperatures cancel, my moles cancel, and I'm left with liters, which is what I want. Okay? So 0.3125 times 0.0821 times 298. What is the volume? $7.64?
7.645.
6.5?
4. Yeah, 5. It rounds 5.
Okay, we'll just say that. Okay, great. Okay. What is the mass of N2 required to occupy 3.0 liters at 100 degrees Celsius and 700 millimeters of mercury? What am I solving for? Okay. Can I solve for grams in the ideal gas law? So what am I going to solve for in the ideal gas law? Moles. PV equals nRT. N equals PV, right? N equals PV over RT. Move RT down. So, my pressure, what do I use? Okay, they gave me pressure in the question. It's the wrong units. So I need to convert it. 700 millimeters of mercury. Okay, it needs to be converted, and 1 atmosphere equals every 760 millimeters of mercury. So I need to convert that from millimeters of mercury to atmospheres from the millimeters of mercury using this conversion. So what goes on top? 1. What goes on the bottom? So 700 divided by 760, what do you get? Whoa. 0.921 atmospheres. Okay, good. So 0.921 ATM here. Volume? 3.0 liters over R. .0821 liter atmospheres. Kelvin moles on top. I'll just move those up there. And what is my temperature? 373 Kelvin. Kelvin temperatures cancel, moles. Oops, I'm sorry. We want the moles. Liters cancel, atmospheres cancel. I'm left with moles. Because otherwise I would have put them down here. Whoops. And whenever you do that, they move to the top. So that's why. So, and that allows them to, you can see how they cancel better that way. Okay. Okay, so what is the moles here? 0.921 times 3 divided by 0.0821 divided by 373. What do you get? N equals what? Moles of N2. But that didn't answer our question. So we want to go to the grams of N2 from the moles of O2, right? So what number do I put on top? That's right. So what is it? I think somebody said it. 28. 28 grams of N2 for every 1 mole of it. 0.09023 times 28. How many grams of N2 do I have? Okay, that's how many grams of N2. 2.53 grams of N2. Yes?
The atmosphere, you don't have like the NFHG. Could it be CMHG?
Sorry, say it again.
Like if the atmosphere is like 700 CMHG, like how would we?
Oh, centimeters mercury?
Convert the ATM?
you would probably put it into millimeters of mercury first. So from centimeters to millimeters. So millimeters is 1,000, centimeters is 100. So you do that conversion first, and then do it to atmospheres from there. But honestly, I doubt you'll ever see that. Okay. Maybe you'll see it. Oh, was it a Connect homework question?
No, it was on
Okay. So mostly you're just going to have to do it from millimeters mercury to atmospheres. That would be the, but yeah, so centimeters to millimeters, that would just be a 100 to 1,000 conversion. Okay. Okay. Now, we still have some more laws. Aren't you guys excited? So we have the ABC gas laws, the combined gas law, we have the ideal gas law, and now we have Dalton's law. But this is the easiest law of them all. Okay? This one's easy. So all that Dalton's law is saying is that the total pressure of a system is equal to all the individual partial pressures added together. You sum them up, and they equal the total pressure. So let's say you had H2, O2, and carbon dioxide, gases. H2 was at a pressure of 0.5 atmospheres. O2 was at 1.5. And CO2 was at 2. What's the total pressure? 4. That's it. That's all Dalton's law is about. Okay? So if you had, let's just say you didn't have O2, but you knew the other things. The total pressure was 4, and H2 was 0.5, and CO2 was 2 atmospheres. What's P2? Well, you simply subtract those from 4, and you'll find O2, right? So this is very straightforward, Dalton's law. Okay? It's just the sum of the individual partial pressures of a gas are equal to the total pressure. So, for example, the atmospheric pressure, the pressure in this room right now, would be equal to the pressure of nitrogen and the pressure of oxygen added together to give us the atmospheric pressure, okay? Which is probably something like 0.98 or 0.976, okay? Close to 1 atmosphere. That's where we're at right now, this partial pressure. Okay, so in reality, everything I told you is a lie, okay? There's no such thing as an ideal gas, just like there's no such thing as an ideal child, okay? They just don't act like you want them to, right? You guys know you were kids. You gave your parents grief. That's how these gases are. They give us grief because they don't act how you want them to. But so what's causing them not to act the way you want them to? The attractive forces between them. So if you have a polar molecule and another polar molecule, they're going to attract, and that throws off the ideal situation. Okay? So they're no longer acting as an ideal gas if there's attraction in those molecules. So nonpolar molecules act more ideally than nonpolar gases act more ideally than polar ones because there's less forces of attraction. Okay? Now, does that mean that we just throw out everything we just learned? No. The calculations are still very accurate. It's just that they're not going to give you the perfect answer. Okay? But they're going to be close to the right thing. And in the laboratory, you're going to consistently get something close using these laws that we just learned about. Okay? But why is it that I don't get the exact answer? Because they're not ideal. They're not acting in an ideal way. And they won't. Okay, so that's gases. Now let's talk a little bit about liquids. Okay? So what are some of the characteristics of liquids? Liquids are virtually incompressible. Okay? You can't compress them. So if I have something that's full of a liquid, I can't just push it smaller. Like a gas, I could. If I had a balloon full of liquid, I could make it smaller. But if I had a balloon full of water, I couldn't force it smaller, right? It would just start going out in all directions or something, right? So it wouldn't work. Which is water.
Well, the first one you said you can compress a liquid, and it's like
Oh, well, you can't compress a balloon full of liquid, so if I said that, sorry. But you can compress a balloon full of gas. Okay? So a balloon full of gas, I could push it closer together, make it smaller, right? But if it was full of liquid, if it was a water balloon, I couldn't do that. Okay? Which is a good thing, because if you guys drove here in your car or rode a bus here, then your vehicle, that vehicle had to use brakes. And if liquids were compressible, then the brake fluid in your brake lines would not work. Okay? So why do you have brake fluid in there? Because it's not compressible. So if I push on the brake pedal, that forces the liquid to push against my brakes, which pushes against my tire, my wheel, the rotor to be exact, okay? And it forces it to stop. But if it was compressible, then I would push and the liquid would compress and the brakes would never compress. Has anybody ever had the wonderfully fun experience of having air in their brake line? You have?
Yeah.
What's that like?
A pain. It's a pain.
Okay. Okay. So if you have air in your brake lines, then when you push on your pedal, your brake pedal, guess what you compress? Not your brakes, you compress the air. And so guess what you keep doing? You keep going. Okay? So you're not stopping. So that's fun, right? It's like an amusement park right there. Yeah. So you can't stop, so you have to, so if you're ever in that situation, which hopefully you never are, but if you ever are, pump your brakes, right? Pump them really fast, and then you compress that air really quickly so you can finally push your brake pads and slow down and stop. Okay? So brake fluid, it's incompressible. Viscosity. Viscosity measures a liquid's flow, resistance to flow. So syrup. Syrup is very viscous. It doesn't flow very easily. Okay? So, but if you heat it up, what happens to it? Now it's starting to flow, right? It's starting to move faster. So as you increase the temperature, it will increase the, or it will lower that resistance, that of the viscosity. Okay? So why? It's the attractive forces. So polar molecules tend to be more viscous because they stick to one another. As they're rolling, they're sticking to one another and they're resisting flow. Whereas if you had a liquid that was nonpolar, a nonpolar liquid, they would just roll over each other and they wouldn't have as much resistance. Now, a lot of nonpolar molecules don't exist in the liquid phase at room temperature because they're gases, like O2 and N2, okay? So it's harder to really conceptualize that, okay? But that's more how it would be. Water, you don't consider that to be very viscous, huh? Probably not. But if you compared it to liquid oxygen or liquid nitrogen, you would probably say, oh, this is very viscous, water. And that's because of its attractive forces. And we're going to look at some of the attractive forces of water in more detail because it's a pretty amazing molecule. And this is one of those, surface tension. Okay? Surface tension is a measure of the attractive force exerted on the molecules at the surface of a liquid. So things that are polar have stronger surface tensions than things that are nonpolar because the nonpolar molecules don't attract to one another. So let me just draw this. Let's say these are water molecules. Okay? Okay, so let's look at one of these water molecules inside of the water, this one. So if we're considering the attractive forces acting on that water molecule, it's here, it's here, it's here, it's here, 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 here. So all around it, all the other waters surrounding that one molecule are pulling it in all directions. Okay? So it's getting pulled all over in one direction. But now let's look at the attractive forces on this water molecule. It's getting pulled this way. It's getting pulled this way, and this way, and this way, and this way.
Is that why like it sits on the top of the spoon?
Why what?
Like you can have water sitting on top of like a glass or something without it overflowing?
Yes. That's exactly why. So you can fill it all the way to the top and then keep going, and it creates this little bubble, right? Because that surface tension is holding it in place. Or a droplet of water. You've ever seen a droplet of water? Why do water droplets form? Because of the surface tension that's in those water molecules, holding them together. Okay? So what's happening is at the very surface, I'm getting pulled that way and down. But I have nothing pulling me up. So it creates a tension on the top of the water. So these are all getting pulled by one another, and it creates a very strong tension across the top of the water. Right? So if you belly flop, there's a tension there. You'll feel it, right? When you hit that water, it's there. And you won't go in until it breaks that